Thanks, Marty. Good morning, everyone, or good afternoon, depending on where you are in the world. Welcome to our group's project, Carbon Cycling Across Spatial-Temporal Scales. Thank you, everyone, for joining us. We're really excited to share what we've been coming up with for the past couple of months. All right, looking ahead, here's our agenda for today. We're going to talk through an introduction and kind of give some background and motivation for the development of our research questions before we dive into some early preliminary statistical methods and preliminary results. And then we'll start with going into our future directions and where we're hoping to take this project. But before we begin, I first wanted to introduce myself and my team members who are joining me either virtually or spiritually today. I'm Taylor Walker, and joining me today are Ricky, Julie, John, Guopeng, Carla, and Ian. And before we get into why we are doing this project, we kind of needed to talk about why synthesis, why carbon. But first, I feel like it's appropriate to talk about the elephant in the room, both figuratively speaking and politically speaking. We've all seen the headlines popping up, NSF, NIH, radical changes to the scientific funding landscape as we know it. And while these times are a little bit uncertain, this is an opportunity to turn lemons into lemonade. And this is where synthesis science really comes in, because this could be an opportunity to conduct hopefully more cost-effective science in an attempt to cope with these fluctuating budgets. And while this is unfamiliar territory now, we did see a little bit of this when we were in the pandemic. We had a lot of scientists sitting at home, twiddling their thumbs, wondering and thinking, man, I really miss science. How do I stay engaged with the research community? And then we started to see this influx of synthesis papers coming out. And one such paper was this Kessler et al., which came out in 2021. And this paper was looking at organismal abundance and comparing them across different LTER sites, which are long-term ecological research sites. And these sites are really rich and really interesting because there's lots of them throughout the United States. They represent lots of different types of ecosystems, and they even extend beyond the United States as well. And this presents an opportunity to compare these different types of ecosystems without actually having to visit these ecosystems. And each of these sites has lots of data that is just ripe for the picking. And so this paper was looking at long-term ecological trends across ecosystems and organismal abundance, and utilizing the LTER site was something that we were inspired by reading this paper. And digging in a little bit deeper as to what this paper did, this paper conducted a moving window study with data sets that are greater than or equal to 10 years in duration. And what I mean by moving window is they took a data set in its entirety and looked at any long-term significant trends or patterns. And then from there, they took a subset of that data set and compared it against the final product. And essentially what they found was kind of concerning. They found that it takes on average 9.7 years to actually reach a critical temporal threshold for data sets that are either 10 years or greater. And so this figure on the left is one from the paper. And what they found for the Kanza Prairie LTR site was that a lot of the subsets of data resulted in spurious results, which are results that either were in significant, which are the red dots, but in the opposite direction of the actual long-term data set in its entirety, or they were insignificant results. And this is really kind of concerning because the short-term studies really are the basis of a lot of the literature that's out there for a lot of different fields. And a lot of this literature really is the information that we're using to make informed management decisions. And if we are not actually capturing these long-term trends, that can be concerning for how we manage these ecosystems in the long run. And so, in essence, this all boils down to short-term studies are not always representative or reflective of long-term ecological trends. But this is where synthesis science really can come in and help shine some light on this and hopefully give us a chance to check ourselves and make sure that our short-term studies are actually reflecting long-term ecological trends. And we could talk about the reasoning behind why studies are so short-term, and that could stem from the average duration for completing a dissertation or a thesis or funding cycles. But it boils down to needing to make sure that we're actually accurately reflecting long-term ecological trends before we provide advice to managers and policymakers. Okay, so we've talked about the why synthesis. Let's talk about why carbon. So in addition to seeing those funding headlines, we've also seen a bunch of different headlines about carbon credits, carbon capture, carbon sequestration. And what this means is that carbon markets and efforts to reduce carbon emissions are becoming increasingly popular. However, our understanding of carbon and the carbon cycle remains limited. There are still large unknowns that persist regarding carbon cycling impacts and whether and how these are impacted by anthropogenic climate change as opposed to long-term natural climate change. And there's also a lack of comprehensive studies that are comparing carbon and carbon cycling across ecosystems, across ocean and land. And also, we know that carbon stocks in particular sometimes operate on geologic timescales, but if we have all of these short-term studies, are we really accurately reflecting long-term carbon trends? And so we hope that by conducting this project, we'll be able to get at how well and how accurately short-term experimental manipulations are actually reflecting real life, long-term ecological trends within carbon across different ecosystems. This leads me to introducing our research questions, which are how do trends in carbon cycling compare between experiments and long-term natural variability? And to what extent does the duration of the disturbance influence how we model carbon cycling projections in the future across ecosystems? And now I think Guopeng will take it away.
Okay, so here are our hypotheses. First, I think, it's very hard to predict the temporal pattern of climate change effects on carbon cycling. So we think all ecosystems will respond identically to long-term changes in climate forcings. And more specifically, if we think about nutrient, um, oh, Taylor, should I control by myself or you can? Okay, yeah, thank you. So if we think about like nutrient addition, we think like the temporal pattern should be dependent on like the resource limitation. For example, in resource limited regions, adding the specific resource can stimulate plant biomass with this effect should gradually increasing over the long term. However, if the regions is not limited by that resource, so if we add that kind of resource, it may result in insignificant or even decreasing effects on biomass over time. Because they don't need like more nutrients for their growth. Okay, so next, we just show you the list we are using to search the data set. So the keywords include carbon, sea, experiment, flux, stock, and like the experimental duration should be like equal to or longer than 5 years. And for data harmonization, there are like four steps. First, we only focus on data with direct measurements, and then did pre we did we like pre-process data set. So we just summarize all data to experimental level, and then the data set is constructed like by column key. And then we just harmonize all data sets to biomass of each type of experimental manipulation. And this table just includes the LTERs we are including for our preliminary analysis. As you can see, we have like 8 LTERs, and the duration is from like 13 to like 36 years. And we have different climate change types, including nutrient warming, CO2, frosting, cutting, and yeah, fire something. And currently, we are mainly focusing on above ground biomass. So next, Taylor. For statistical analysis, we just calculated response ratio. For example, we just use biomass under climate change divided by biomass under control. So And if the value is greater than 0, it means climate change can increase carbon cycling, such as biomass. But if the value is smaller than 0, it means climate change can decrease carbon cycling. And this figure just shows our preliminary results about the temporal pattern of climate change, such as such as nitrogen addition on above ground biomass. And we just show you like 3 LTRs. And as you can see, the temporal pattern is very different across sites. And I think, yeah, we will do more like analysis to include like the data from more LTRs. But as you can see, these 3 LTRs do have very different climate variables and also different ecosystems. For Cedar Creek, we can see overall like nitrogen effects on biomass decreases over time, but for Sevilleta, the effect is like relatively stable. But for Niwot Ridge LTR, so nitrogen effects actually increase over time in the long term. So it can be because of different ecosystem times, different climate variables, and different intensities of nitrogen inputs. So yeah, our plan is to include more data from other LTRs to consider the roles of climate, soil, and ecosystem variables in the temporal pattern of nitrogen or like climate change on carbon cycling. So basically, we will include like more climate change types, such as climate warming, drought, and something. And currently, we are only focusing on above ground biomass. So we will include maybe soil carbon and soil carbon efflux in the future data analysis. Yeah.
Thanks, Guopeng. So after listening to those preliminary results, we also wanted to kind of share our reflections on how our project's been going so far and our interactions with Seeker. And first, we wanted to talk about what went well. I think all of us in our group and maybe others in Seeker really enjoyed like pitching our individual projects before they started to become group projects and kind of formulating our projects and refining our projects and getting to bounce off ideas off of our fellow Seeker fellows. And then also really enjoyed the biweekly trainings, the data wrangling, and the group management tools were super, super helpful in helping us thrive as a group and helping us get all the tools that we needed to move forward with our projects. And then we also wanted to talk about what could be better, both within our group and maybe across Seeker. But I think our group in particular really struggled with and found challenges within trying to narrow our scope. So I think in the future, being more decisive, I think early on would have helped us a lot. And then also harmonizing all these different types of carbon data sets and whether they were fluxes or stocks was really challenging. There's a lot of different types of response variables that are reflected across all of the LTR sites, and trying to remedy these and harmonize these was definitely a groan zone, as Seeker would call it. Um, so in terms of next steps, we're hoping to eventually stop data acquisition, which I think we're pretty much there now, and stop data harmonization. And then we're going to start creating more figures, hopefully incorporating more response variables into those figures and also more LTR sites. And then hopefully start manuscript drafting sometime this year. And then I think our group can continue communicating effectively and continuing to refine our project scope and question to make sure that we're accurately addressing those questions. And then here's just a timeline of where we see this project going. So we'll probably be doing data cleaning, harmonization, and more statistical tests throughout the summer. And then in the fall, start really putting out those figures. And then in the winter, early winter, we'll start discussing like or drafting methods and discussion and really drafting that manuscript, and then hopefully sending that manuscript to our individual lab PIs for internal edits before we send it off for a journal for consideration. And with that, we like to acknowledge everyone, all the secret team. Thank you all. Gabe, I'm so sorry your picture's not on here, but it is on the next slide, I promise. Thank you, Marty, Nick, Carrie, and thank you to our mentors, Will and Marci. We really appreciate all of your guidance and all of your help in training us and giving us the tools that we needed and the advice that we needed to move forward with this project. And then we also wanted to send a huge thank you to our fellow Seeker fellows. And Gabe, I'm sorry, I lied. You really want taking the picture. So I lied. I'm sorry. And thank you, and we'll open it up for questions.
Thanks so much, Taylor and Guopeng. Much appreciated. For webinar attendees, please. Oh, Megan's got an actual question. Go for it, Megan.
This was really great, and I'm glad you guys are off making a lot of progress. There's been a lot of syntheses on how biomass production or AMPP is impacted by all these different global change drivers. And I'm kind of curious, what's your unique angle? What are you adding new to the literature here that hasn't already been synthesized before? Thanks.
Sure. Thank you for your question, Megan. So we showed above ground biomass for this particular presentation because we felt like it was one of the easiest things to harmonize at first, but there's a lot more response variables that we're actually hoping to incorporate in this analysis. Soil carbon, respiration, photosynthesis are among some of the ones that we are looking at. So I'm hoping that in addition to looking at biomass as a stock, we'll be able to incorporate more flux variables that will hopefully make the study a little bit differentiate the study from what's already been published about biomass specifically.
Thanks. More questions? I was curious, you're moving into figure generation this summer. What variables are you planning on starting with there? And how are you hoping to reconcile the different patterns that Guopeng showed in his portion of the talk?
Guopeng, do you want to take this or do you want me to?
Yeah, so I can take this question. So yeah, I think this is a very great question, and I think currently, we only have a few sites. So I think in the near future, we will include more data points. So this allow us to, come to determine the roles of climate and soil variables in their temporal pattern. For example, I also did some simple linear regression to determine the nitrogen effects decrease, increase, or doesn't change significantly. We plan to use the slope of the simple linear regression, to do further analysis. For example, if it's a significant correlation, so the slope can be 0.8, and the other one, if the temporal pattern is a decreased trend, so maybe it's negative 0.7 or something. If we have 20 sites, we can do something like meta-analysis. We have weight factor. We consider other factors, and we finally we can have a value to see the overall temporal pattern, if it's increase or decrease. And also we will include mean annual temperature, precipitation, ecosystem type, and other factors to see if the temporal pattern is regulated by these factors. So this is my plan.